Hello everyone, welcome back to a new OK video. My name is Omar and let's jump right in. In this video, we are solving the question titled Minimum Path Sum. In this question, we get a grid as an input. We require to find a path between the top left corner and the bottom right corner. Each cell contains a cost and the path we want to find is the one having the lowest cost. The trivial solution would be to run all the possible paths and calculate their costs and see which one is the minimum. This is not optimal, and there are paths which overlap, making us recalculate a lot. So, we will solve this question using dynamic programming. If you already know what is dynamic programming, you can skip ahead. What is dynamic programming? Dynamic programming is a fancy word for a problem-solving technique. The idea of dynamic programming is that you have a big problem you want to solve. You assume that you can reach a solution for a smaller subproblem. All you need to do is define a transition or an operation to jump from that smaller subproblem to the big problem. So, dynamic programming needs three things to work: a state, transition, and a base case. Let's get into more details. A state is supposed to be the solution to the problem we have at hand. Normally, this state is represented and saved in some sort of an array structure. Then, the previous locations in the array carry the previous state. Then we have the transitions between the previous states to this one. It is normally a simple operation between them. The whole trick in dynamic programming is finding this transition. This transition will be repeated throughout all the subproblems and eventually reaching a base case. The base case is what represents the smallest possible problem that we can have. Then it is like block building over each other. Well, this awfully looks like recursion thinking. So why don't we just use recursion? Well, one of DP advantages that it tries to optimize for recursive solutions. In recursion, there might be overlapping subproblems, meaning these subproblems are required in several steps. In recursion, we go and recalculate the subproblem solution again and again and again. Using dynamic programming, we save the state in our array to avoid recalculating this solution. This approach can optimize a solution from running in exponential time to linear. So the first step is defining the state. We will create a 2D array of the same size as the input to store the states. Each cell will contain the minimum cost to reach this cell. Our final solution will be in the bottom right cell. So what is the transition between state cells? Remember, we need to have a simple operation between previous states and the current one, which will give us the correct shortest path to this cell. Since it is stated in the question that we can only go down or right, we know that to reach this cell, we either came from the above cell or the left one. There are no other ways to reach this place. So, if we take the shortest path between these two and add the current cost, we will be sure that this will be the shortest path to this current state cell. Just to put in mind, the first row does not have an above cell, so the shortest path is simply the one from the left. Also, the first column has the same property, where the only path can come from above. So with this, we finally have all of the rules of the transitions between states. What is missing right now is the base case. What is the simplest problem we can get? Yes, a 1x1 grid. We use our top left cell as the base case, where the cost to go to it is the cost in the cell itself. Then we simply build up on that using our rule, and we will find our solution in the bottom right corner. So let's implement our solution. We start by initializing m and n as the dimensions of our grid. We create a variable called state, which will carry the cells we mentioned. For the start of the state or the base case, it is the same as the grid. For the first row, we use only the value from the cell to the left. And for the first column, we use only the value from the cell which is above us. For every other cell, we see which one has the smallest cost, the top or the left one, and add it to our current cost. And finally, we return the bottom right cell value. So now let's test this. It looks fine and passes the tests. If you notice for this code, for each state cell, we add the corresponding grid cell too. To optimize the space, we can use the grid itself as the state, doing the operations then on itself. So here I will simply exchange every state variable with grid and refactor the code, and that's it. This will reduce the space consumption from O of m multiply by n to O of 1, since we didn't use any extra space. So let's run the tests again. Looks fine. Let's submit. Perfect, it passes all of the tests. As a bonus, I implemented the brute force solution so you can see the difference in performance. And guess what? It exceeds the time limit. That was all for today. See you in the next one.